Above this, here is, I allocated regular task F, the one and only time F will run, and then I terminate it down here. By the way, the termination time is exactly the original time, the starting time, plus the number of time steps we dictated in the code by the set cycle time statement. So we wanted F to run maybe 30, so here is 30 bigger than this one. What is this? Oh no, F I think was, how many? No, here it is. 436 and 401. So F was 35 times units of time. So this is just fine. So that's the last time I want to look at the log file. We looked for log file on problems. But today we are not going to have any problems. So we don't want to look at the log file again. Let me just turn it off. The real file I want to look at is, like I said earlier, rc_utilization.csv. But before I look it up, I want to change the number of cores from my preset of 2 to 64. It will be more interesting. So what I do is, this is the run button, by the way. This does the same as the run as. So I click on it. If I click on it, you see, let me bring the, yeah, you see it's running again and finished. But next time I don't have to say run as, I can just click this run button, run task. But to the right of it, there is a little pull down arrow. I'll pull down on it, and I select not the first one, run as, but the second one, run configuration. Change the configuration of the run. I do this. And by the way, I want to go to the slides again. Here's slide number 17 headed. You see this slide show changing the number of processing cores. Go to this pull down and then select run configuration and then select arguments and put the argument down here. -n, no space, and the number of cores. So this is what I'm going to do now. I'm going to my machine. I'm selecting here, I already did the pull down. I'm selecting arguments, and it says -n2. That space to change this into 64. That's it. And now I don't have to save anything. I just click on run, goes. And now it will compile again. Everything is okay. And run the program, bang, 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 bang. The emulator takes about the same time to run. It just needs to execute all these tasks, all these instances sequentially, so it doesn't matter what number of cores I ask for. Now I have to do the refresh again. So I refresh my screen, and then I go to rc_utilization.csv. I double click on it, and the right thing happens. It starts, it doesn't open inside Eclipse. It opens into the program, the Linux program, the Open Office that handles CSV or Excel-like files. And it says text import, CSV is text, text import, where is it? Right away, here it is. And I make sure that the encoding character set is Western Europe something, otherwise it doesn't understand it. And then I just click OK. So the code is the LibreOffice Calc, which is the Excel-like thing. And here I get everything. And what I get is recording not like the log file, which recorded each and everything, but here I have an entry every time the number of active instances changed. So, for example, This is the first unit, the first time where there were 16 instances of F, what is this, F, and, no, not F, B. 16 instances of B and 48 instances of D. And the next row is the last time that this was true. And this ends in 24. Next one is 25. Immediately next time step, I get a different number of instances because the scheduler here is extremely efficient. In one cycle, it changes the number of instances without any delay. So this is nice in order to draw a graph. So I draw the graph by clicking this, first selecting everything. And then you see this red pie charts on the top. That's for drawing the charts. So I click on it, and it offers me just default chart, which is bad. That's not what they want. So I'm going to select X, Y scatter. Comes up, the menu comes up automatically. X, Y scatter. And then out of all these, I select the line chart. So I click on line chart and say finish. And this is what I got. Very interesting chart. Very useless. It's not really what I want. And the reason is, let me just, come on, increase it or move it a little bit aside, and then, what is it? I can draw it like this. Put it like this, here. You see, on the left is number of active cores. And for a long time, what I get is just one. This one is the useless, there's no information in this activity. RC scheduler, configure task. This was a task that just set up everything, and it really interferes with our measurement. And everything else happens almost instantaneously at this time. Okay, so this is not bad, not very good. So let me delete this and go back to this table. So you see RC scheduler config task, I don't want it. I select the whole column by clicking on the top of the column, right click and say delete selected column. Done. But the time is still there, you see 0, starting at time 0, and nothing really significant happened until the first number, which is just a random number. By the way, these numbers change from 1 to 1. They are they are an effect of what Linux does in a virtual machine on top of my Windows machine, which have no clue on real time, or no clue on process time. They give you real time, and it depends on what my rest of my machine was doing. For example, the antivirus and the internet and whatever. So it has nothing to do with my game. I don't want it. So I'm also clicking on number 2, row number 2 here. And then right click on it, brings me the menu, and I say delete selected rows. Now I get real data in some relative timing, and I don't care about these numbers under the time column. Mark everything again and go back to do the chart. And now again I select in the menu that comes up XY scatter and line and finish. And now I get what I want. So this is a very nice picture that tells me what kind of parallelism I managed to get. Come on. Not every, my wireless mouse doesn't work, but the tablet on my laptop does. So now I get it. What do I see? I'm still stuck with the relative numbers on time numbers on the x-axis, but that doesn't really matter. What I want to look at is to get a general idea. By the way, I put the same chart in the slide, and in the slide, I made it a little bit better. So the next slide say execute, run, refresh, view the log, and then view the utilization. That's what we did. And in the utilization, I here got the text instructions, accept text equal, select the Western Europe character set, select all, create the chart, and there's a useless access scheduler config task, it takes too long, delete it, and reach out, and this is what I get. So this is the chart we have gotten, and it had 4 rounds. So I marked them with these arrows. Of course, these arrows don't come up with Excel or this Linux tool, but they are very nice to do in PowerPoint. So here they are in PowerPoint. 4 rounds. The round starts with A. A is just a little thing here that goes up to 1 because it only uses it's a regular task. It uses 1 core. Immediately after that, up to C, I start B. B is the green one, and it just really fast, short time and small number of instances. It uses all 64 cores, and it does, one set after another of 64 instances until all instances are exhausted. Maybe at the last round, at the last iteration, it will not be 64 because I think there were 2,000 instances, and 2,000 does not divide into 64 into an integral number. So there is the last round will be maybe 16, I think it showed. So the Excel table showed, oh, the last time I'm running 16. And 16 is, but you don't see it here. So it appears as if it was nicely divided, and we have 64 cores running B until exhausting all the 2,000 instances. And then come, after A, we could start in parallel, by the way, we could have started in parallel B and D. Remember the task graph from here, B and D. And indeed, we could have done B and D in parallel, but the scheduler does not like it. So it schedules all instances of B first, and only after that it schedules all instances of D, although they could have run in parallel, but there is no point in running them in parallel. They are concurrent, I can run them in any order. Scheduler is simpler by just doing all B's first and then all D's. When the last few of B's are running, 16 of them, 16 instances, then the remaining 48 instances are D already. So at the last step, they run in parallel. By the way, why do I start with B's and not with D's? Because in the task graph, the row for B is written first. The line for D is written next. If I wanted to change this, I change the order. I put D first, and only after that B, and then the scheduler will, they don't care, it's all, they are concurrent. The scheduler will run all B's first, all D's first, and then all B's. So, yeah.
Question, I'm a software guy.
Yeah.
For the sequentiality of the task graph, the first regular A says it's equal to D, which only happens once, of course the count is false. But isn't the count false the entire time that it's running until it counts to 4?
No,
what makes
no. So count, you see, count need to run only after E, but that's a very good question. So you say you're not a software guy, but you asked a perfect software question.
Because in the graph it's sequential.
Now let's go back to the left. You see count function, and it says round counter plus plus. When I'm saying count is executed once, increase round counter once, and disappears. Later on, it gets executed again, and again, and again. Who remembers the variable round counter between iterations of invocations of count? And the answer is, look up. a round counter is a global variable. It's not defined inside the function count. It's defined globally. It doesn't go away. So you execute count, it accesses this global variables, count disappears, finished, but the global variable is preserved. So the only thing that preserves the state of the count is the global variable round counter. We know it's global because it's defined in a code above all the functions or all the tests.
But the return stays 0 for the whole time.
Yeah, no, return is, so that's good. So the return value is given to the scheduler uses it, and then it disappears. Next time it generates a new return value, it's given to the scheduler exploits it and throws it to the dumping. So return value is not global. It just happens once. Every time you call count, a new return value is generated and given to the scheduler, and that's it. So return is generated every time new. Round counter is global variable, single global variable, preserve the value from one round to another, from one loop to another. Okay? Good. Very good question. So all these are executed here, and then after these are done, the C's can be executed. C was depending on B, but D came first. And then all E's execute. And at the end, F is executed, well, count is executed also. In red, we hardly see it. And then F is executed here. Very briefly, and a new round is starting with the new set of B's, green B's going on. And it's done 4 times. Okay, so back to, well, next slide. Reading the time report. So this is an example of the time report. By the way, we see here that B was executing on 64 cores for a long time, doing many instances. A long time is, here I take the difference in time cycles. I just created a new column in the spreadsheet and computed the differences between successive time values, and I got 464 here and one there, 465 units of time. B were executing on 64, and then 16 were left to run during 15 units of time, 14 plus 1, and at the same time I could already start 48 units of D, and then once B is completely exhausted, D goes up to using all 64. And then C. So C starts here with 8, and then 24, and then 64, and then 60, and then 44, and then 36. Very interesting changes because of how many numbers there are. Since I can only have 64 here, 8 here, they start at different times, and then by the time I finish, they don't all go at the same time, so the finishing time is taken off in small number of cycles. But, so these are the total numbers, and this is the total work. What is work? So C takes 20 cycles, that's defined in the code, and 2,500 instances, going back to the code to remind ourselves, here is C, 20 cycles, defined. And here is C, needs to run 2,500 instances. So 2,500 instances, each of them need to run 20 cycles. The amount of work is the total number of cycles spent by all instances of C. Here it is computed in the chart. So work of C is the total number of instances times the time it took. So 8 instances were executed for 14 cycles here, and 8 times 14 is 112 total cycles that were spent on C. And so on and so forth, and I accumulate all of them, and I get 50,000 by the spreadsheet. And here the computation confirms that I need 50 cycles, because I wanted 20 cycles each times 2,500 instances. The total is I need to spend, doesn't matter on how many cores, all in all I need to spend a total of 50,000 cycles. If I wanted only a single core, I would get pure 50,000 cycles, because it will just take 20 and 20 and 20 and 20 until we accumulate. So this shows that indeed the emulation makes sense. Every little piece of time here, it's executed on a different number of cores, whatever is available, but the total number of work done is 50,000 cycles. And again, why was it like this? First, I only had access to 8. Then I had access here. Same goes with these guys, you know, with D. It needed 40 at the last page, so here I can only release 24 cores for C, and they were used. And here this is completely finished, so I can go take all 64. But now I've exhausted all of them after 759 cycles. I exhausted all tasks, and I only have remaining 60 tasks. They continue on 60 cores. And then 16 have completed, and I need, I'm left with 44. And after these 5 cycles, you see 1 and 4, I'm finished with another 8, and I'm left with 36. And they run for additional 5 cycles and gone. So this is really nothing mysterious here, and no undeterministic numbers. It's all very simple. I have to do this work, and I schedule this work, and they start in a staggered fashion, so they end in a staggered fashion. That's it. Very simple. And only after all of C's are finished, I can start here with 64 cores executing E, and then on and on. So that's what's happening there. So let me get out of this. Yeah, and back to the real thing. It logged me out in the meantime. So I log back in again, and I'm still in the same place. So what I've shown on the slide are additional columns here. Of course, I can do anything here. I can say diff, and in the first one I'll put a 0. There's no difference. But in the second, yeah. So the last bullet here says speed up. Speed up is another feature. T1 is the time to run this program on a single core. By the way, we know what T1 is. T1 is this number. Where is my pointer? This. 856,095. Because this is the total work that was done. And if I ran it on a single processor, this is the number of cycles that it would take. So T1 is 856,095. Divided by speed up for 64 processor, divided by the time it actually took on 64 cores. And this is this number, 13,496. So if I divide one by the other, I get 63.43. This is a very good return on investment. I use 64 cores, and I run it 63.43 times faster than on a single processor. And we will show programs where this is not the case. It's very hard to achieve. The last Well, I will show later, after the break, how we investigate speed up and efficiency for these number of cores, and I can change the numbers, and these are powers of 2, from 1 to 1024, only 11 of them. Speed up is this, work efficiency is this, and so on. And I can draw this graphically, so I did this work. It took me 10 minutes of running and copying the value to an Excel spreadsheet. So P is the number of cores, and all I need to copy is the total length of time, and then I compute speed up and efficiency. And I draw them on this chart. So this is a log-log chart. The bottom is 1, 2, 4, 8, the number of cores. It's, as you see, it's logarithmic scale. On the left, it's a logarithmic scale of speed up. And speed up is the red chart, red line. And it shows, you know, speed up is very nice. Even on 1024, I get 838. So it's very close to, but not the same as 1024. It's actually efficiency of only 0.82. The blue line is ideal speed up. So 1024 would be 10, the speed up would be, ideal speed up would be 1024. And you see the red line covers the yellow line, sorry, the blue line, except at the very far end. And the green line is efficiency, No, the total runtime, TP. What is the runtime on here? Efficiency, by the way, if I drew it, would be just look like a straight line of 1, and it was a little dip at the end. So this is the runtime, and it's very nice, almost a straight line in a log-log chart. And of course, we'll see later that we don't get there. So why we want to do this, and why we look at other numbers, and how we do it, that all comes later after the break.